I wanted to take a little bit of time to talk about two problems. One of them is number 39 from your book, and the other is number 45 from your book. And both of these problems introduce techniques for solving that I wanted to focus on. The first one introduces a technique that all of you should know how to do, and that is to solve an equation using the calculator or using the quadratic formula. The second one is more advanced and is something that I want to show you that physicists and other scientists do, but you won't necessarily see on a test question. So with that said, let's get started on number 39. A helicopter is ascending vertically with a speed of 5.2 meters per second. At a height of 125 meters above the earth, the package is dropped from a window. How much time does it take for the package to reach the ground? And then they give you a hint. The package's initial speed equals the helicopter's. So we do our usual. We're going to create a reference frame for ourselves, and I like having the ground be 0 and up being plus. And in our particular situation, the package begins life 125 meters above the ground. And according to our hint, the initial speed of that package is upwards at 5.20 meters per second. So we now take in mind this problem for the initial information. Of course, the V0 is easy. And because the package is falling, its acceleration is easy also. And finally, if we reflect on it, we see that the package is going to start up here at y0 equals 125, and it's going to fall all the way down to a final y of 0, so its displacement, or delta y, is equal to negative 125 meters. And what they're asking for is the amount of time that it's going to take for the package to reach the ground. So we reach into our grab bag of the equations of motion for constant acceleration and see that this one is going to be very nice for us. Delta y equals v0t plus 1/2 at squared. Now, substituting all of the numbers in, we get negative 125 is equal to 5.20 meters per second t. Pardon our units here, that's negative 125 meters. And over here, plus 1/2 of negative 10 meters per second squared. Cleaning this up just a little bit, we get negative 125 meters equals 5.20 meters per second times t minus 5 meters per second t squared. And this is the equation that we have to solve. All of this so far has been very straightforward problem solving. The problem that we run into now is how do I solve this quadratic equation? And I recognize that it is quadratic because it involves the variable t squared. Algebraically speaking, we have three options. Only one of them is going to be viable for us. Graphically, we have the graphing calculator option, which is always on the table for physics students. So let's break these down. Taking you all the way back to Algebra 1 or maybe Algebra 2, you remember that when we had a quadratic equation, we had three solution options. Factoring, in which we appealed to the zero product property to say that if my quadratic factors as x minus r1, as x minus r2 equals 0, then one of those factors has to be equal to 0. That option is my favorite option for solving quadratics in general, but I look at this 5.20 right here, and I think to myself, I am never going to be able to factor that thing. So factoring is probably not a good bet here. The second option was completing the square. And completing the square is a really useful technique, but physicists don't like it so much because it requires a lot of intricate arithmetic. And every time that you complete the square, you end up doing exactly the same operations that you would if you used the quadratic formula. So the quadratic formula is going to be our option of choice for solving quadratics if we're going to do them algebraically. And the way the quadratic formula works, you may remember how this goes. We start off with an equation in standard form, ax squared plus bx plus c is equal to 0. And then through the magic of completing the square, we discover that x equals negative b plus or minus the square root of b squared minus 4ac. And my students, all over 2a. And my students that are in my math classes learn a little song that goes along with it, and I won't sing that at you now. But it always goes through my head. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a, etc. Well, in this particular case, if I apply the quadratic formula to our equation, first I need to put it in standard form. So I'm going to take the equation that we have, negative 125 equals 5.20t minus 5t squared, and I'm going to add 125 to both sides and rewrite the terms so that they are in decreasing order of degree. So that I now can identify my A, B, and C. And this gives me now t is going to be equal to negative b plus or minus the square root of b squared minus 4 times a times c. All of that over 2a. And when I simplify, then I'm going to end up with two different roots. One of those roots is going to be mathematically impossible because it will be negative, and it will refer to a time before the problem started. That's a time that's not really modeled by our equation. But the positive root that we get, which turns out to be 5.55 seconds, is going to be our answer. You can check, by the way, that this works out. So if I'm doing it algebraically with the quadratic formula, first I need to know the quadratic formula, helps to remember the song, and then I need to put my equation in standard form and find the root. Not difficult, takes a little bit of practice to get all the numbers in the right places and not to make stupid mistakes. Alternatively, you can solve it on the calculator, and the calculator solution to this equation for any equation always goes the same way. y1 equals the left-hand side, y2 equals the right-hand side, and we find the intersection point of those two sides with second calc intersect. Let me demonstrate that at this time. If I pull up the calculator here, and I am going to let y1 equal the left-hand side of this equation, which is negative 125, and I'm going to let y2 equal the right-hand side of that equation. Oh, somehow my negative sign didn't happen. Try again. There we go, which is 5.20. The calculator doesn't know any variable other than x, so I'm going to write that as 5.20x minus 5x squared. Now the only tricky part about this is I need to set my window size so that everything is visible. And in particular, when I set my window size, I need to make sure that my y values include negative 125 because my y1 was equal to negative 125. So let's make y range be from negative 150 all the way up through maybe 50 or something like that. And that's going to cover all the distance from the ground up to past the top of the helicopter. And then for the x-min and x-max, I don't know how long it's going to take for the object to hit, but I know it won't be less than 0 seconds. And I figure 10 seconds has got to be safe for 120 meters. And so I set that window size like so, and I graph. Here comes y1, here comes y2, and y2 represents the package falling, y1 represents the ground, and where the two intersect is where the package hits the ground. Second calc intersect, first curve is y1, second curve is y2. Put the cursor close to the intersection point and hit enter, and we get an intersection point at x, which represents t, 5.5 seconds. All that you have to show on your page would be the equation and the solution. No other algebra is needed. So I hope this is helpful to you. This gives you two options, good options for solving. Algebraically, if you really want to do it, I recommend the quadratic formula. And graphically, if you want to do it, y1 equals the left side, y2 equals the right side, second calc intersect. The second problem that I want to take a look at is problem number 45 from your book. And this is a more sophisticated problem. It's going to involve the technique of successive approximations. The idea is that we're going to approximate the solution to our problem, and then we're going to use that approximation as kind of a rough draft to get a better approximation to our problem. Here we have, a rock is dropped from a sea cliff, and the sound of it striking the ocean is heard 3.2 seconds later. If the speed of sound is 340 meters per second, how high is the cliff? Okay, we need a picture, we need a reference frame, and I'm going to take down to be plus and the top of the cliff to be 0. And we also need to have a clear understanding of what's happening. The rock is dropped at time 0. Here comes my rock. And it's going to fall all the way to the bottom. And when it does, sound waves from that rock are going to come back up. When they come back up, they're going to come back up at a constant 340 meters per second this way. So our motion really happens in two parts. And in the first part, part 1, the acceleration of the rock is going to be negative 10 meters per second squared. The initial velocity of that rock is going to be 0. The time is unknown. The final velocity is unknown. And the delta y is also unknown. So we are missing one piece of information to make this happen. Meanwhile, in part 2, the sound comes back up to us with no acceleration. The speed of sound doesn't change, at least not because of gravity. And an initial, or a velocity, a constant velocity of 340 meters per second. The delta y, the time, are also unknown, but the delta y here is the same as the delta, equal but opposite to the delta y there. This is the key insight. Delta y here is going to be positive. Delta y here is going to be negative. So this is opposite delta y as it goes, as the thing goes back up. Okay. So with all of this said, we have two options in front of us. One option that I do not recommend is we could use the part 1 and the part 2 to set up two equations in two variables, delta y and t. Notice that we would say something like t rock plus t sound all add up to 3.2 seconds. And we can now write some kind of equation for t rock and some kind of equation for t sound. This sounds like a bad idea to me because it seems like it's going to involve a lot of complicated algebra. The second way that I could approach this problem, though, is very clever. And it's going to start with the observation that the time that it takes for sound to travel the cliff at 340 meters per second is going to be a lot less than the time that it takes for the rock to fall. this double inequality means T rock is very much bigger than T sound. And so what I'm going to do is I'm going to estimate that T sound is basically 0. It's not really, it's going to be a small number, but we're going to estimate it as basically 0. And I'm going to compute the height of the cliff based on the simplifying assumption that the sound takes no time at all to travel. So if I do that, the setup is actually really easy. Delta y is equal to v0t plus 1/2 at squared. I dropped the rock with an initial velocity of 0. The acceleration is the acceleration due to gravity. And if I'm assuming that the sound took no time at all, then the rock took 3.20 seconds to fall. And based on that assumption, I can now do a calculation, a relatively simple calculation, and find that delta y is equal to negative 51.2 meters. So this is my first approximation based on the simplifying assumption that the sound took no time at all. Now, let's consider that to be a rough draft answer. The cliff is 51.2 meters high. And let's now do a second draft of our solution by asking, okay, if the cliff is 51.2 meters high, how long will it take the sound to travel upwards at 340 meters per second? And that's an easy calculation. Here comes our second approximation. We're going to say that the time that it takes for the sound to travel is going to be the distance, 51.2 meters, which is pretty close, divided by the speed of sound, which is 340 meters per second. And when we do, we find that the amount of time that the sound actually travels is 0.15 seconds. Now that's not 0, but it's close enough to 0 that I can see that my simplifying assumption was not very far off, and so the true height of the cliff is going to be pretty close to the 51.2 meters. If T sound is 0.15 seconds, then T rock is going to be the total time minus that, or 3.05 seconds. And if the T rock is actually 3.05 seconds, then I can compute again delta y equals v0t plus 1/2 at squared, or minus 5 times 3.05 squared. Remember that v0 is still 0. And when I do this modified calculation, I get a new revised speed or size of the cliff is 46.5 meters. This is now a second draft answer, and it is much closer to the true value. How close to the true value? If I really wanted to, I could check this by doing a third draft in exactly the same way. I could find T sound based upon my new updated information of 46.5 meters, the negative sign there, divided by 340 meters per second. And that gives me 0.14 seconds as the amount of time that it took for the sound to travel back up. Notice that my third draft answer and my second draft answer are practically the same. So that T rock is now going to be 3.20 minus 4, or 3.26 seconds. Excuse me, 3.06 seconds. There we go. And that makes more sense. So that delta y for our third draft answer is going to be negative 5 times 3.06 squared, which is 46.8 meters again. this point, because my third answer and my second answer are so close that I'm going to take the 46.8 to be the true answer, or as close as I need to be to the true answer. And I'm going to say that the cliff is 46.88 meters high. Honestly, if you had stopped at the second draft answer, I would have been okay with that too. So what is the moral of this story? The moral of this story is that when we have two quantities that are being added together, like the time for rock and the time for the sound, and one of those quantities is significantly less than the other quantity, you have physical reason to believe that, then it makes a whole lot of sense as a first draft answer to pretend that the smaller quantity is basically zero. And do your computation. And if you need a little bit of refinement based on that, then you can take your first draft answer and create a second draft answer as we did. Notice that the difference between our first and second drafts was almost 5 meters. So that's a real difference. But our difference between our second and our third was only 0.3 meters, which is not very much difference at all.